In this video, we're going to talk about the different types of transistor amplifiers, such as the Class A amplifier, the Class AB amplifier, the Class B amplifier, and the Class C amplifier. There's also the Class D amplifier, but we're not going to touch that one in this video. So let's draw the circuit for the Class A amplifier. We're going to start with an NPN transistor. This is the base of the transistor, that's the collector, and this is the emitter. We're going to connect the emitter to a resistor which we'll call RE, the emitter resistor. RB is the base resistor, and then RC, the resistor associated with the collector. Now RC and RB, they will be connected to VCC, the collector supply voltage, which will be the positive terminal of the battery. And then typically there's another resistor, which we'll call R1. RB and R1, they form a voltage divider. Now the capacitors C1 and C2 are coupling capacitors. They're used to block DC, but they will pass an AC signal. And then we have the ground. And then typically you'll find connected across the emitter resistor is a bypass capacitor. It allows the AC signal to bypass the emitter resistor, thus increasing the voltage gain of this circuit. So here we have an input signal, and then at the output we're going to have an inverted but larger output signal. And so the function of an amplifier is to increase the power level of an AC input by transferring power from the DC power supply to the input signal. The voltage gain of the amplifier is the ratio of the output voltage to the input voltage. The efficiency of the amplifier is the ratio of the AC load power divided by the power delivered by the DC power source times 100%. So this is the Class A amplifier, also known as the common emitter amplifier. It has a maximum efficiency, that is a maximum theoretical efficiency of 25%. The actual efficiency will usually be less than that, but that's the maximum theoretical efficiency. And so as you can see, this amplifier is not very good in terms of or being used as a power amplifier. It's more appropriately used as a small signal amplifier because its efficiency is so low. Now this particular transistor conducts for the entire 360 degrees of the input cycle. So Q1, which is this transistor, that's a terrible circle, is always on in this case. One advantage of the Class A amplifier is that it has very little to no distortion, which is good, even though the efficiency is very low. Now, in order to design a circuit with an efficiency that is close to 25% as possible, you want to set VCE, that is the voltage between the collector and the emitter pins of the transistor, to 1/2 of the collector supply voltage. So if the collector supply voltage is 9 volts, you want to design a circuit in such a way that VCE is as close to 4.5 as possible. Now keep in mind, VBE, the voltage between the base and the emitter, is going to be between 0.6 and 0.7 volts. And IC is equal to beta times IB, where beta is equal to HFE. Beta is the ratio of the collector current to the base current. So those are some things that you want to know when dealing with the Class A amplifier or the common emitter amplifier. Now there's something that you could do to increase the efficiency of the Class A amplifier. And in order to do that, you need to replace RC with another element, that is a transformer. And so what we have here is a transformer coupled Class A power amplifier. So the output is going to be across the secondary part of the transformer. What you could do is replace it with a load resistor if you want to. And so with this particular transformer coupled Class A amplifier, the theoretical efficiency is no longer 25%, but the maximum theoretical efficiency is 50%. Now, to actually achieve this is not easy. In actuality, your actual efficiency might be less than 40%. You might be getting efficiencies of 35%, 39%, or something like that. But the maximum theoretical efficiency is 50%. Now, here's a question for you. Why is it that replacing RC with a transformer increases the efficiency of the circuit? Why is that? It has to do with the fact that the transformer, like an inductor, can absorb and release stored energy using its magnetic fields. Let's set the collector supply voltage to 12 volts. Now, keep in mind, the input current is fluctuating. So the base current is fluctuating, and thus the collector current is fluctuating as well. As the collector current increases, the magnetic field that is generated by the transformer, that field is going to increase in strength. And so during this process, energy is being stored by the transformer. And so there's going to be an induced EMF generated by this transformer. At this point, the transformer is absorbing energy. And just to keep things simple, let's say that the potential across the transformer is 8 volts. So these two voltages, they go against each other. So at point C, the voltage will be 4 volts with respect to ground. Now, the current won't increase forever. Eventually, the current is going to come back down. When the current decreases, the magnetic field collapses, and that stored energy is released back to the circuit. The polarity across the transformer reverses. And so this is now positive, and the other side is negative. And let's use the same value, just to keep it simple, 8 volts. So now the potential at point C will be the sum of 8 and 12 volts. So it's going to be 20 volts. So notice that the potential is higher than the collector supply voltage. And as a result, this increases the efficiency of the transformer coupled Class A amplifier circuit. Now the next type of amplifier that we're going to talk about is the Class B amplifier. The Class B amplifier, it uses two complementary transistors, an NPN transistor and a PNP transistor. Let's call this Q1 and Q2. So Q1 is an NPN transistor. You can easily distinguish it from a PNP transistor due to the fact that the arrow points away from the center of the transistor. In a PNP transistor, the arrow points towards the center. Now we need 3 resistors, one of which will be between the bases of the 2 transistors. So we're going to call this R1, R2, and R3. Now the input signal is going to be coupled through 2 capacitors, and it's going to be connected to the ground as well. The output is going to be taken across the load resistor. And here is the collector supply voltage, VCC. So this is the circuit for a Class B amplifier. The maximum theoretical efficiency for this amplifier is 78.5%. Now, in order for this circuit to work properly, the 2 transistors have to be biased at cutoff. During the positive half cycle of the input sine wave, Q1 conducts. So Q1 is in the on state, Q2 is off. Now, during the negative half cycle, let's put this in blue, Q1 is going to be off and Q2 will be on. So for each half cycle, only one of the transistors should be conducting if it's designed appropriately. The other transistor should be off. So each transistor conducts for 1/2 or 180 degrees of the sine wave. And so this improves the efficiency of the Class B transformer, the Class B amplifier. Now there's one problem with this particular circuit, besides the efficiency not being 100%, and that is crossover distortion. The output doesn't look like a nice pure sine wave. Instead, it looks something like this. My drawing is not perfect, but that's what it is. Now the crossover distortion is created due to the fact that the emitter base voltage of each of the two transistors is approximately 0.7 volts. So until the input sine wave reaches positive or negative 0.7 volts, the two transistors will be off, and so the output voltage will be 0 at this point. So that's the one disadvantage of the Class B amplifier, is the presence of crossover distortion. Now this circuit can be improved by creating what is known as a Class AB amplifier. And to create the Class AB amplifier, what you need to do is replace R2 with 2 diodes. And these are silicon diodes with a voltage drop of approximately 0.7. So to combine, the total voltage drop between, let's call this point A and point B, will be 1.4, which is equal to the voltage drops of the two transistors, which is also 1.4. Now granted, the voltage across the silicon diode and the base emitter junction of a transistor both can be between 0.6 to 0.7 volts. So this could be 1.2 and that could be 1.2, but they're relatively close to each other. The combined voltage drop will be somewhere between 1.2 and 1.4. But that's how you could design the Class AB amplifier, is by replacing R2 with 2 silicon diodes. And so this will reduce the problem of crossover distortion. So that's the advantage of the Class AB amplifier. Now the last amplifier that we're going to talk about today is the Class C amplifier. This particular amplifier only uses one transistor. It's not like the Class B or the Class AB amplifier that uses 2 transistors. Now, this amplifier is different from the other ones in that it is a tuned amplifier. So it has an inductor and a capacitor in parallel with each other. So we'll call this C2, this is C1, and we'll call that L1. And then we have a resistor, RB, and that is attached to a negative voltage, which we'll call negative VBB. So that is the Class C tuned amplifier. The efficiency, the maximum theoretical efficiency for this amplifier is pretty high. It's 99%. However, there's a major disadvantage with this amplifier, and that is the distortion. The distortion can be very severe for this particular amplifier. And the second thing is that it conducts for less than 180 degrees of the input cycle. So during the positive half cycle, that is when it's above 0.7 volts, this side is going to be positive, this side will be negative. Conventional current will flow in this direction, charging C1, activating the NPN transistor. And when that's activated, current will flow from the DC power supply, charge in C2 and L1, and then oscillations will begin. Energy will be transferred back and forth between C2 and L1. And so that energy transfer happens during the positive half cycle. During the negative half cycle, Q1 is off. If we put a negative sign here and a positive sign here, current cannot flow in this direction because the base emitter junction will be reverse bias. And so Q1 is off during the second half, but it's on during the first half when the voltage exceeds 0.7. So it conducts for less than 180 degrees of the input cycle. So that's the Class C amplifier. It has a lot of distortion, but the maximum theoretical efficiency is very high. Now, I've seen different variations of the Class C amplifier. Here's another one. And depending on which variation you're using, sometimes the efficiency could be 80%, 90%. But it's still relatively higher than the Class A and the Class B amplifier. So RB is going to be connected between the base of the transistor and the ground in this case. We're still going to have a capacitor, and instead of an inductor, we're going to use a transformer this time. And so the output will be across the transformer on the other side. So we'll put a low resistor here. So this is another variation of the Class C tuned amplifier. So that's another way in which you could design the Class C amplifier. The resonant frequency of the tuned circuit is going to be 1 over 2 pi times the square root of LC. Well, specifically C1, and then you got to find out what the L value is for that side of the transformer. So that's basically it for this video. Now you know the difference between a Class A, Class AB, Class B, and Class C amplifier. Thanks for watching.